All right, let's go ahead and get started. Welcome, everyone. Happy Monday, and congratulations on making it to week 3 of AI Summer. This week, we'll start with just wrapping up a conversation about all the different model types we've seen so far, and a short presentation by one of our master's students and DSSG fellow, Shahan Kwang. And we'll kind of take it from there. But before we get started, are there any questions, lingering questions that people have from our conversations from last week? All right. If there are no questions, I'll quickly go over our agenda for today. We'll start with a quick session on diffusion models, after which we'll talk about how we can work with secure data, confidential data, stuff like that. And we'll talk about how we are able to run and host local models using two applications called LM Studio and Anything LLM. I'll be putting links to download these two applications in the chat in a minute. And if you can do that while our next presentation takes place, that'd be great. And we'll kind of do a quick walkthrough through those. And then Miranda will go over LangServe and a quick intro to backpropagation to prepare us for our conversations on Wednesday, where we'll really get into the nitty-gritty of fine-tuning these large language models. So I'll put these links in the chat while Shahan gets his screen set up.
So can anyone see my screen up right now?
Yes, we can.
Well, let's get started. So good morning, everyone. My name is Xiaohan Kwang, and I'm currently a master student at Data Science Institute. And I'm honored to be invited to talk about the fascinating topic of diffusion models and how we've applied this concept in our research projects. Let's dive in. So before we dive into the diffusion models, let's review at how artificial intelligence has evolved, showing here in this evolution tree. So over time, we've reached an exciting point with generative AI that it can create new data like sounds, code, images, videos, and text from what it has learned before. So the key idea is that the generative AI can make the new data based on the existing data. So the diffusion models are a special type of generative AI that creates new data through a process like inference, not just prediction. So in this graph, you can see that the diffusion models are actually a subcategory of the generative model. So now let's explore some of the most exciting applications of diffusion models. So one standout is stable diffusion, which has gained a lot of attention. I'll show you how I implemented and use the stable diffusion on my own laptop, and you can try it by yourself later as well. So in this simple experiment, I asked the model to draw a cat in a space outfitted in an aerospace suit. As the model goes through each sampling step, it gradually removes the noise from the image, improving its clarity and detail. This process highlights the diffusion model's ability to refine and enhance the image incrementally. So let's continue our exploration of diffusion models by looking at how they work using a natural phenomenon called the Brownian motion. So imagine you are adding a single drop of red ink into a glass of clear water, and over time the ink spreads and the clear water gradually turns red. And this movement, driven by the random collisions of particles, is a core principle behind the diffusion model. Now let's apply this concept to diffusion models. The diffusion model works through two main processes, the forward process and the reverse process. So think of the forward process as adding layers of digital noise to an image, similar to how the ink drop spreads in the water. Eventually, the image gets completely covered by noise, just like the water turns fully red. The magic happens in the reverse process, where the model learns to remove the noise step by step, revealing the clear image underneath. It's like rewinding the ink spreading in the water, like using a time machine, gradually restoring the image to its original state. So to understand the underlying mathematics of this process, let's talk about a little of the Markov chains. So a Markov chain is a model that describes a sequence of possible events where the probability of each event depends only on the state of previous event. So this sounds like a really hard math concept, but let's use a simple example to understand this concept. Imagine you are tracking the weather. If it rained yesterday, so there's a certain chance that today will be cloudy or raining or sunny based on past patterns. We can visualize these chances with arrows connecting different weather states, each labeled with a probability. So given this complete graph, if it was cloudy yesterday, so then there's 70% chance of sunshine today. We can predict today's weather by looking only at yesterday's weather conditions. So given all of these conditions, if we have a sequence of days with different weather, so how do we predict tomorrow's weather? So suppose day 1 was cloudy, day 2 was raining, and day 3 was cloudy again. So what's the probability of day 4 is sunny? Well, the answer is quite straightforward. We only need to look at the weather from the previous day. By checking yesterday's weather, we can use this probability to predict today's weather condition. So as you can see, we can only look at the weather conditions in day 3, which is cloudy. So we can get the probability directly from this graph, which is 17%. The same idea applies to diffusion models in both the noising and denoising processes. Each step in adding or removing the noise depends only on the previous step, just like predicting the weather with a Markov chain. Now we understand how Markov chains work in adding and removing noise step by step in diffusion models. Let's talk about the score functions. The score functions help by showing the directions to reduce noise in the images. So this leads us to the score-based diffusion models, which use these directions to clean up the images and create clear, high-quality results. The figure on the left-hand side shows the Swiss row distribution, and each data point in the Swiss row is a two-dimensional coordinates, and each data point is joined from an underlying data distribution Px. The goal of generative modeling is to train a model P theta x that approximates the true data distribution Px. After successfully modeling the P theta x, it allows us to sample new data points that follow the original data distribution. The model P theta x can be expressed as the following math formula. However, directly computing the z theta is often intractable because it requires estimating the probability of every single point in the entire space and make sure that the integral of all of the probability of every single point equals 1. To bypass the z theta, the score function of the distribution P theta x is defined. So in a score-based diffusion model, instead of directly approximating the probability distribution Px, we construct a model that learns to estimate the gradient of log probability density function, denoted as the gradient log Px. One significant challenge in learning the score function is that not having enough training data in some regions of the distribution. One way to solve this problem is to involve the true data distribution into some known distribution, like the normal distribution. Through this process, the data diffuses across the two-dimensional space, filling in the knowledge gaps and allowing the model to obtain information from the empty areas. Here is the framework of score-based diffusion model. In the forward step of the diffusion process, we gradually perturb the data distribution by adding Gaussian noise. The step is governed by a mathematical equation called the stochastic differential equation, or SDE. Here, the first part of the SDE, dx equals fxt dt, is an ordinary differential equation. And the second part, dw, represents the white noise. And w here, as we mentioned before, is the Brownian motion. fxt and gt are hyperparameters in the SDE. And in the special cases, we can set the fxt to 0. So this SDE has numerical solution. So we can calculate the data distribution at any time step t. At each time step, we train our neural network to approximate the score function. The score function can be visualized as a vector field, showing on the right-hand side. These vectors indicate the direction of data points should go. By following these vectors, the data points can move through the space and find their most favorable position. During the forward diffusion process, we generate a large amount of data, and from this data, we train the neural network to approximate the gradient of log px. The loss function in this is the L2 norm between the two vector fields. Once the neural network is well trained, we can integrate the score function into the reverse SDE. In this reverse process, fxt and gt are known, and the score function is trained. By solving the reverse SDE numerically, we can sample new data from pure noise. This means that given pure noise as input, we can generate new data that follow the original data distribution. Without the SDE, it cannot learn the score function in the region where there are less training samples. So we've also prepared some simple examples of score-based diffusion models using the Swiss row data. You can try this out by running the Jupyter Notebook on Google Colab. And let's take a brief overview of these examples. And if you are interested in the detailed math behind this, you can check out the paper or the blogs linked in the reference section. So let's take a quick review of this tutorial. Yeah. So in this tutorial notebook, firstly, we retrieved the Swiss row data. The detailed definition and steps are denoted here. By the way, I'm not going to dive into the concept of variance preserving and the variance exploding techniques that help the model to learn all of the possible data distribution. It's relatively a hard concept and may need a lot of time to explain. Well, let's continue.
Xiaohan, could
Yeah.
you zoom in a little bit?
Zoom in.
Mm-hmm.
Okay. Yeah.
Great, perfect. Thank you.
So let's continue. So as we mentioned before, the fxt and gt are hyperparameters and can be manually defined. Defined loss function is here, and it follows the mass formula. And we compute the loss by the L2 norm between two scores, the true score and the score predicted by the model. So as you can see here, the score here is the score generated by our neural network, and the gradient log p is a truth score by calculation. And finally, by using the a proper reverse SDE, we can sample the data from a pure noise, and eventually it will become the known distribution as a Swiss row. So, well, let's get back and continue to next part. So how does the diffusion model work in biology, especially in molecular docking or some other cases? So the molecular docking is a method of computer-aided drug design. It simulates the binding process of small molecules and the macromolecules. We can predict the binding mode and affinity to ligands and receptors, and it's mainly used for drug screening and optimization. During the binding process, the ligand must effectively compete with and replace the water molecules to secure its position. So if we decompose the binding energy into the enthalpy and entropy terms, nearly half of the energy terms are related to waters. So that's one of the most important reasons that why we want to explore the water molecule distribution around the protein surface. So in our project, we implemented the score-based diffusion model to learn water molecule distribution around the protein surface. Each water molecule is treated as a single point so far. The forward and reverse process in the project are similar to what we've discussed before, but they occur in the 3D space. The key challenging is processing the protein data. For our project, we constructed here three different graphs for each data for each protein. So the protein graph, the water graph, and the cross graph. The cross graph represents the interactions between the water molecules and the nearest protein atoms. During the training process, each graph is processed by E3NN to generate a token representing the graph. So E3NN here means the equivariant 3D neural network. It means compared to the traditional convolutional neural network or CNN, the equivariant neural network can learn the graph in a 3D space regardless of the translation or rotational change. So for example, if we have an image of dog, the traditional CNN can learn the dog images and give the response and to recognize this image as a dog. However, if we rotate the dog image, the CNN have to learn it again to know that it's a dog, it's the same dog as before. So so this issue can be resolved by the E3NN because during the training process, the E3NN can learn its rotational and translational changes of all of the graph. So by gathering all of these tokens as inputs, we obtain the score in the 3D space. Here are some preliminary results from a model with fewer parameters and a smaller training dataset, giving the protein surface and the water molecules randomly distributed in the 3D space. As you can see, the water molecules knows where they should go and they accumulate on the protein surface. So to enhance the accuracy and coverage rate, we are currently training a more complex model with 3,000 training data sets and using all item models. And I think that's all for the introduction of diffusion models. And thank you all for listening. So do you have any questions during these slides for our project? No? Great. Yeah, thank you all again.
All right. Thank you so much, Rohan. Okay, so now let's get back into our agenda for the day. So we just did diffusion models. Now let's talk about working with secure data. So as we've kind of briefly mentioned before, by default, conversations with ChatGPT and the APIs often tend to get reused for training of future models. So any conversations that you have with ChatGPT, they might get used to train GPT-5 or 4.0, which is the latest model. So when you are working with any data that's confidential on pretty much any level, it becomes important to start thinking about alternative approaches, because clearly you don't want your confidential data to end up as part of GPT-5's training data set. So in general, the main two approaches that we have when it comes to dealing with secure data is either using some sort of enterprise contract with OpenAI, Google, Microsoft, Anthropic, or we kind of change direction and we start looking into open source models. These are models like Llama, which was introduced by Meta, and Mixtral, and Google's Gemma, just to name a few. So this is the data classification guide that's provided by Vanderbilt's Office of Cybersecurity, and they've kind of broken it up into 4 different levels. And this is a good sort of schema to follow in general, even though maybe your company or organization's actual data classification would be slightly different, but generally our sort of AI solutions for each of these categories of data would be probably about the same. So we start with non-sensitive data, level 1 data, which is usually intended for public release or distribution. This would be open source data sets, government data sets, anything that you can download from the internet and you don't necessarily care if it ends up on the internet. And this would work for a lot of researchers, but say if you're working with patient confidential data or anything else that you may not want the public to see before you publish your results, you'd probably want to look into a different solution. Level 2 is documents that are usually institutional use only. These could be things like unpublished research data, institutional documents like blueprints and HR data. And these are just generally data sets that should be private to the institution or have been made available to individuals with specific permission. Level 3 data is a little bit more restricted. It's usually bound by some contract or law and should never be shared with unauthorized persons. This would include data sets protected with NDAs, HIPAA information, patient health information, FERPA, GDPR, DUAs, all that sorts of good stuff. And finally, there's level 4, which they define as critical, which is also bound by contract law. But usually this tends to require some like bespoke security requirements. This would be classified data sets, law enforcement records, generally stuff that you would probably receive explicit guidelines to work with. And so you got to be very, very careful when working with stuff like that. So when you have these different types of data sources, what kind of tools can you use? So if you're level 1, non-sensitive data, everything that we've talked about so far is good to go. You can use the embedding models, the chat models through the UIs and the APIs, no problem whatsoever. Institutional use is when we need to start thinking about alternative approaches. And this would vary by your needs, depending on what you're researching and how comfortable you are with your research data possibly ending up on the internet. You can choose to go down a variety of different routes. So if you might have noticed sometimes on the ChatGPT UI, you might notice the option to opt out of allowing OpenAI to use your data, use your conversations for training. That is a kind of very low level kind of barrier that OpenAI provides. If you really are concerned or if there are any sort of contracts involved, I would not use that option. It's definitely not something that gives you guaranteed protection for your data, but it is something that you can use if you're maybe working with synthetic data or something that's a little less confidential. You can also sign up for an OpenAI team account. That too gives you a little bit of the same sort of protection where OpenAI kind of just blanketly states that, okay, we won't use your data for training, but you don't necessarily have some sort of contracted obligation from OpenAI that's preventing them from using your data. It's just, personally, it feels like an honor system. The other option would be institutional access and enterprise contracts. This at Vanderbilt, we have something called Amplify, which is available on the website vanderbilt.ai, which I'll briefly show in a minute. And this is essentially a contract that Vanderbilt has with Microsoft Azure and Anthropic and Amazon Bedrock, which allows you access to all sorts of models with at least level 2 access. And I'll show you which models that covers. The most foolproof solution always will be an open source model. These are models that you can download from Meta, Google, like Llama and Gemma. And essentially what you're doing is downloading the model as a whole. You're going to follow the guidelines provided by Meta and Google to use them. But they're good models where anytime you use them, nothing is getting sent out to the internet. All the inferencing is happening on your device, so you don't need to worry about the type of data that you're using. That being said, you still need to be aware of where you can store your data. So for level 2 data and onwards, you're probably going to want to store your data on Acre or other approved storage solutions. This will include things like OneDrive, Google Drive, any sort of cloud storage that is password protected. When you're starting to think about maybe vector stores and you're trying to maybe set up some sort of RAG-like infrastructure, you would either want to use a local vector store, so you'd be creating that vector store locally and saving it as a whole somewhere using local embedding models, Or you can use a hosted vector store, which is also password protected. But again, the specifications of this will depend on your specific needs. And then finally, if you were trying to fine tune one of these models or train them, you'd again want to train on something that is somewhat password protected. So you could use a Google Colab depending on your needs, or obviously the best solution would be to use some sort of private server like Acre or the DGX A100s that the DSI has. Moving on to level 3, this is where you pretty much get into the zone of using only open source models or specific enterprise contracts. So Vanderbilt is currently in the process of providing access to GPT-4 and Claude and Mistral at a level 3 secure access. It is currently in process. They have the architecture set up, but they're just waiting on sort of Vanderbilt to kind of sign off on it. So we should have that soon. But generally, best practice would be just, if you can and you don't need the power behind some of these larger models, go open source. Similarly to level 2, you would want to store your data on Acre or private servers. This is likely not data that you're going to want to store on something like a Google Drive. And similarly, you want either local or approved vector stores, and then you want to train on Acre or some sort of private server. Would not recommend Google Colab. Finally, level 4 critical, if you're working with any sort of classified data or law enforcement data, you're probably going to want to stay away from anything that is not open source. There are no plans to provide access to GPT-4 or any of those models at a level 4 secure level. So open source or custom models and custom data solutions are the kind of direction that you're going to have to go in. Before I kind of do a quick demo of Vanderbilt.ai, are there any questions about this general setup or questions that you have about your own data sets and are wondering where they might live? Cool. So let's take a quick look at Vanderbilt.ai. Let's see. All right. So here is Vanderbilt.ai. You can go to this website. If you are a Vanderbilt staff, faculty, student, you should have access to this. You might need to create an account the first time, but you'll pretty much sign in with your Vanderbilt account. And then we have access to all of these models. So GPTs are provided through Microsoft Azure, and then Claude and Mistral are provided through Amazon Bedrock. And by default, all of these provide you access, level 2 secure access, with level 3 coming soon, although level 3 might only be something that's restricted to Azure. And let me just pull up my chat to make sure I'm not missing anything. We have a question. Are de-identified MRI images considered level 2 or level 3? Do they need to be extracted to be level 2, remove everything but brain from image? This would, again, depend on the guidelines provided by maybe your IRB or maybe you as a researcher. If you are comfortable putting that stuff if you think it follows the guidelines of level 2 as per Vanderbilt cybersecurity, I would say that would be fine. Generally, we've been able to use de-identified MRIs and X-rays and treat them as level 2. But there have been cases where, depending on your IRB, you might need to consider them as level 3. Cool. So coming back to this, what this essentially is a chat GPT-like interface that covers multiple different models. And you get all the sorts of custom tools that you might be looking for if you're trying to build some solutions. So you can change the temperature, which makes the model outputs from more precise to creative. You can change the response length. And also built into Amplify is a RAG infrastructure. Although you don't really have that much control over exactly how that infrastructure works, this would be a good place to maybe test out your level 2 data before maybe building a custom solution to see how these models work. You are also able to provide custom instructions. You are also able to create assistants. This is a feature that is currently in process, in development, but essentially this would work somewhat like an agent. you are able to create it, but we don't really have too much information about this yet. And you can also always set prompt templates, default custom instructions, and so on and so forth. As always, you're able to also keep track of your chats, share this with other users across Vanderbilt, work in specified workspaces that you could share with other users, and export and import conversations. Great. And this is free to use for all Vanderbilt users up to a certain limit. I think if you pass that limit, Jules might reach out to you and try and talk to you about possibly finding a paid solution for this, but it is an awesome resource for Vanderbilt researchers. Shane, you have a question?
Yeah, when you said that there's a built-in RAG infrastructure, do you mean we can upload documents using the plus down there by the prompt, or is there another place if we want to
Yes,
just...
exactly. Exactly. You can hit the plus here and add files, and then you can also, once you upload a file, it kind of saves them in your like workspace environment. So this is a text file that I'd uploaded a couple months ago, and so I can still pull this up and pull that back into my chat.
Great, thank you.
There is a question about assistance in Amplify. Direct trainings, yes. I think they do have monthly sessions, which I think gets sent out over email. So you might be able to get more information about assistance there. Other questions? Cool. If you have other questions, just put them in the chat. One of us will definitely be sure to answer those questions. So I think maybe we can take a quick 5-minute break right now. What I would love for everybody to do during this break, if you haven't already, download LM Studio. We'll be taking a quick look at this. It's available in Windows, Linux, and the Apple Silicon Macs. Not on Intel Macs, but if you have an Intel Mac, just feel free to follow along. And then also download Anything LLM. This is also a solution that helps you build custom RAG infrastructures without having to program. It's a great way to kind of do everything open source, but not have to program. So those are some solutions that we will see in a few minutes. But let's take a break until, let's see, 9:40, and then we'll come back and talk about these two.
Hi, Uma.
Yes,
Quick question. What's the state of the videos right now?
I believe the recordings are now in the repo.
They are. Okay. Beautiful. Thank you.
All right, welcome back. Hopefully you were able to download LM Studio and Anything LLM. I did see that some people were having issues downloading this due to VUIT security settings. If you are unable to download this, that's totally okay. This is something that you can follow along pretty easily. And then if you do determine that this is something you would like to have later on, VUIT has been pretty good about enabling access for certain apps. So you should be able to reach out to them. Cool. So what we're seeing here is LM Studio. So what this is essentially a very nice application that allows you to run and host models locally. So this would be all your open source models like Gemma, Mistral, and Llama. As you can see here, I have already downloaded Llama 3 8 billion parameter instruct. So what this is basically an instruction fine-tuned version of Llama 3, the 8 billion parameter version. If you haven't already, I would go ahead and download one of these models. This one is about 5 gigabytes, but there are smaller models. Doesn't matter what model you download for now. But you can pretty much search anything here. One thing I'll point out is that these are all search results from the Hugging Face hub. So any models that are available on Hugging Face will be models that are available to you. So say you had a custom model that you want to be able to run through this, you can simply upload it to Hugging Face and you'll be able to find it here, assuming it is publicly available. Another thing that I'd like to point out is that you might find that there are multiple versions of the same model over and over again. So what these are essentially quantized versions of these models. Model quantization basically executes operations with lower precision, which essentially squeezes the model down to a smaller size, but it comes with a little bit of loss in performance. So like a Q2 is 2-bit quantization all the way up to, for some models, 8-bit quantization. So the 2-bit quantization model will be the smallest and the fastest, but it will also likely be the most inaccurate. That being said, quantization doesn't make your model entirely terrible. It just makes it slightly worse. And we'll talk about this a little bit more on Wednesday and Friday. But what I've done right now is I've gone ahead and downloaded the 2-bit quantization 8 billion parameter Llama 3. And what I'm going to do is going to go into this AI chat section. And what I'm going to do is load my model. So what this is essentially doing is loading a model into memory. As you can see, now it's saying RAM usage is 3.36 gigabytes. What this is doing is just essentially loading my model into memory so I can start using it. So as you can see, there's a lot of things going on here. The important things to look at are, first of all, Llama 3 comes with its own system prompt. If it prompts you to update the prompt according to Llama's system prompt, you're probably going to want to do that. Essentially, this comes along with the model. It helps it work the way that Meta wants it to work. You can also see that context length is something. You can see that DOT supports up to 8192 tokens. That means Llama 3, you can update this to 8192. This will now ensure that all the tokens are used and the model just doesn't cut things short. You can also modify the temperature. The tokens to generate is actually just a maximum. It's a maximum number of tokens that the model would generate. -1 basically means that it will allow the model to determine when it has ended a response, but you could also put in a certain number of tokens here to limit your response to a certain number of tokens, so you can keep track of cost if that was a factor. You can also look at other inference parameters like top K sampling, top P sampling. These are also things that change the way the model decides to figure out what the output should look like. And you can kind of look into the details of all of these. They have really good explanations of what these do. GPU settings, I like to put everything entirely on the GPU. What this does is make sure that the model inferencing is a lot faster. Everything is being done on the GPU. Nothing's being done on the CPU. Your ability to do this will entirely depend on the type of GPU that you have. Here I can see that I have Apple. I think I'm running on an M1, M2 GPU. So it's able to load the entire model into memory, but if you had maybe a smaller GPU, that might be something you won't be able to do. You can also look at things like prompt formatting. This is going to be something that is individual to the model that you're using. Things like this are useful to know when you're actually getting into the world of fine tuning, because you need to know what the prompts are actually formatted like. And there's a couple of other settings in model initialization, such as keeping the entire model in RAM, which is on by default, using flash attention, which makes these models a lot faster, and rope, which is a method that allows models to sort of become a little bit better at dealing with longer sequences. We will talk a lot more about this in detail on Wednesday and Friday. But essentially what this is a very UI-based way to deal with these models rather than have to program, which is very, very useful if you're trying to just experiment and not build a custom solution from the ground up if you're just starting. Another thing I'd love to point out is the model inspector. This is just sort of the metadata that comes along with the models. You can see how many parameters it has, the embedding length, the context length, the architecture. This is just good stuff to know about the model. And again, all of this is going to be happening on your computer. None of this is going to the internet, so you can pretty much put any sort of data that you want. So I can just say, introduce yourself, and then this will load the model and run it all on the computer. Interesting. Efficient language learning U. I've never seen Llama say that before. But again, this is the quantized version of Llama. If you were to use the full version of Llama, it will probably not give you a weird response like this. So let's see. Cool. So there is also a playground in LM Studio, which is essentially a place where you can load up multiple models and pipe their outputs into each other. So if you were maybe using inputs from Llama to do programming because Llama is really good at programming, and then you want to use Gemma for something else, you can sort of pipe all of that through and work with multiple models at the same time. I'm not going to do that because I'm actually not on my computer right now, and I don't have enough memory to deal with that. And with Zoom, it'll probably crash. So I won't demo that right now, but I will demo the local server. So this is essentially hosting your model. So say you have it running in LM Studio, but you want to be able to actually use the model through some sort of coding interface or use it in as part of a RAG infrastructure, or just any infrastructure that you're creating from scratch, but you want the model to be running on your own computer and not elsewhere. This is what you would do. Essentially, you can hit start server, and what this is doing is it's creating a local host, which if you were to copy this is essentially where the model has been hosted, and then you can essentially use it like any other model using the OpenAI code that we've already seen before. So here's a Jupyter notebook, and we've seen this before. You're importing OpenAI from OpenAI, you're using OpenAI, and you're giving the base URL as where the model is hosted. You can change this. You can change this to localhost, whatever you want. API key is just going to be LM Studio, and now this will function exactly the same way as the OpenAI API works. So you have the model, you have to give it the name, and then the message, the system content, the user content, the temperature, and then just print the completion choices 0 message. All looks familiar, but this is a great way to kind of use the OpenAI API code for pretty much any model that's running through LM Studio. So very, very powerful, and you can do a lot with this here. Questions about this so far?
I had one question. So, you know how where you're saying client.embeddings.create?
Yes.
I remember in older versions, you would have just client.create or things like that. Does that change based on which model from LM Studio you're using, or?
It does not. I think this might be an updated or older version of the OpenAI API Python package, but as far as I've seen, everything tends to work exactly the same.
Cool, thank you.
Other questions? Cool. And then, as always, all those sort of server model settings that we were setting up here during the regular chat can also cascade into this. So you can set the temperature here, you can set the context length, all the GPU settings to ensure that the model works the way that you actually want it to. Another super nice thing is that it also collects server logs and saves them into a file by default. So anything that you do, any questions that you send all get sort of recorded somewhere. The question, can we set up these locally executed models to run an API like we worked with last week? Yes, essentially that is kind of what it's doing because you are using the API code. So this is essentially running the model on a web server somewhere, and that somewhere happens to be your computer, and then you can just use the API code to use it the exact same way as you would ChatGPT. Other questions?
So can this also be used in production, or this is just for trying, testing, and
So this could totally be used in production, as I said. So once you have the code here in a Python notebook, you can access this model to do pretty much whatever you want. So you can use this along with LangChain and then call the model and then make a chain out of it and then do all of that same stuff that we were doing yesterday in just a Python notebook or just a Python script. And you can call the model from here. The only thing would be that you would need this server to always be running. So maybe you'd want to run LM Studio on a machine that's sort of always on, but I wouldn't say this would be like production level, but you could definitely run like a small app off of this.
and if it's secure, if it's built on a computer that is secure, and so it will also be secure. No one will access it except the people who have access to that server, right?
Yes. So like if you were to go to localhost 1234v1, you would obviously not be able to see this because it is only running on like my internal network. You could run this elsewhere in a network that other people have access to, and then this would be something that you can kind of see elsewhere.
Thank you.
Cool. So going over to anything LLM. So essentially we still have this server running, but now by default, LM Studio does not have the ability to create any sort of RAG infrastructure or an agent. It's just a way for you to run and host models. There's not much more that you can do apart from just chat with them. So what if I wanted to do something a little bit more advanced? That's where anything LLM comes in. So this is a fresh installation of anything LLM. It might look a little bit different from what you're seeing. I think the first time you open the app, it has like a different startup window, but you can click through that and end up in pretty much the same spot. But essentially what you want to do is create a new workspace, and I'm going to just call it demo. And then I'm going to go click on this little wrench at the bottom. And this is all the settings that will be there for this workspace of mine. So the first thing I'm going to do is LLM preference, and I'm going to select LM Studio. I'm going to give it that base URL that I had originally, which was localhost 1234/v1. It will automatically load the model that you have running. And then you can also provide the 8192 context window. Somebody said anything LLM looks like it is a paid product. I downloaded it this morning, so I don't know about that, and I did not pay for this. So perhaps the link that I sent you all was not correct, but maybe someone on our team can kind of look into that and direct you in the right direction. But essentially what this is doing is basically using LM Studio as an API provider. The model is hosted there, and now I'm able to access it. Some other cool things to note here would be that there's a built-in text-to-speech support, transcription model, which uses Whisper by default, and you can also, for all of these, choose what transcription model to use, what text-to-speech model to use. It uses everything that is system native by default, but you can pretty much do whatever you want here. As you can see here, it's using Whisper small, but you can go to OpenAI and use Whisper large. And also for embedding, it's currently using a built-in embedding model, but you can also use OpenAI. If you have an enterprise hosted OpenAI solution from Azure, you can also use that. So this would be, say, if Amplify gave you an API key, since they are working with Azure, you would be able to kind of use that level 2, level 3 access model through here as well, technically. And then LM Studio, Olama, and all these sorts of providers are available for pretty much every single thing that would use an LLM. You also have power over what the text chunking should look like, what the overlap should look like. So all of these things that we've seen before as part of the RAG infrastructure, you are able to change here just in a UI. You are also able to select a vector database. We've been seeing Chroma as part of LangChain because that's freely available. LanceDB is something that anything LLM provides by default, but there's also other things like Pinecone, Quadrant, all of these things that are also available on LangChain. So you can kind of modify this to your liking. Also, the great thing is it keeps event logs. And if you wanted to, you can also connect your API keys to Hugging Face and OpenAI and your Pinecone databases. You can put those in here and also be able to sort of set this up to work with the OpenAI API without actually having to do any programming. Questions about this so far? Cool, moving on. So going back here, now essentially what I have is this demo workspace. I'm going to create a new thread that I can talk to, that I can kind of have a conversation with it. It gives me the option to upload a document or send a chat. So if I wanted to do RAG, I would click on upload a document. Here, I've already uploaded one that's cached. So again, this keeps history of documents that were previously uploaded in this workspace. So I can click on this and I can say move to workspace. So this is the Declaration of Independence. It's just a PDF. And I can hit save and embed. It uses the embedding model that anything LLM provides, and it puts it into the workspace for me to use. And so now I can just simply ask a question. Let's see, who were the signers of the document? And I can send that question, and it's going to do RAG now. It's going to look at that document, and it's going to pull that information. It's going to be a little bit slow, but it will eventually get there. There we go. And yeah, the document that you're referring to is the United States Constitution. Should be the Declaration of Independence, but it will produce an answer, and this is all happening locally. If you had a faster GPU, this would be faster. And again, you can see that it is actually using the document, it's citing it, so we know that it is actually performing RAG. Another thing to look at is there's a couple more settings that we can work with here. If we click on the little gear icon, here we can see more chat settings. We can change the LLM providers from here as well. The more important thing that I want to point out is that they have a chat mode and a query mode. So chat mode essentially will provide answers with the LLM's knowledge and the documents that you provide. If you're just in query mode, it will restrict itself to only the documents information. So there is a query mode refusal response. So you can say there is no relevant information in this workspace to answer your query. So if it did not find the answer in the document that you had uploaded, it's just going to say no. And similarly, you can set temperatures and all that good stuff and vector databases. Here you have a little bit more control over how many context snippets, how many chunks are getting retrieved. I can set this to pretty much as many as I want, but they do recommend 4. And then you can also look at the similarity thresholds where you can say high, medium, or low similarity thresholds. You can look into what the similarity threshold actually is by looking at what vector database you're using and what kind of similarity scores they use. Those similarity scores tend to differ from vector database to vector database. So you're going to want to figure out what this should look like for your needs. And finally, super, super cool thing, which is brand new as of maybe 2 weeks ago, is a agent configuration. So essentially you can make an agent here without doing any programming. You can make a selection. I can say I still want to use, I still want to use my LLM from LM Studio, and then I can enable a variety of different skills. By default, RAG, summarization, scraping websites is on by default, but you can also generate charts, which is a sort of code interpreter-like situation going on. You can generate files, you can do live web search, you can use a SQL agent. All of this is good, and you can add your SQL connection here. So very, very, very powerful, no programming required whatsoever. So it's a really good way to kind of get started with large language models if you don't have that programming background. One thing I will say is that, and they point out here as well, the specific LLM provider and model that will be used for this workspaces agent. And it says the performance of LLMs that do not explicitly support tool calling will kind of limit your accuracy. So I know that Llama 3 8 billion instruct is not trained to use tools. So if I were to go back to this, or if I were to create a new thread, update the workspace agent, if I were to create a new thread, I am able to call my agent like this, and then just say, I don't know, tell me a joke. It will invoke the agent, and it will continue running it. We can exit it if we want to by just typing exit. This will probably result in a response that is not what we're looking for, just because Llama 3 does not know how to use an agent. There we go. Oh, it did actually, but I can pass on a tool's response from another agent and then it created a joke. So it does kind of work, but not as well as you would hope. So if you were to maybe connect ChatGPT into this, which you can, you'll be able to use this agent a lot more powerfully without doing any programming. So questions about all of that? Cool. If there are no more questions, I will hand it over to Miranda, and she will walk us through a couple more things.
All right. Hello, everyone. Go ahead and share my screen here. Okay, so hopefully you can all see that, and we are going to pivot a little bit from secure data. And sorry, let me get my setup. Cannot talk and do this at the same time. Okay, so we're going to pivot a little bit to, we talked about secure data and setting up on your own machine or using some sort of secure server for your data. And now we're going to look at what we can actually do to deploy these solutions, whether you want to keep it secure or not. How can we actually deploy these solutions? How can we make an app? We're not going to go into much detail through that because it really depends on what you want to do. But we do want to highlight this new tool that is now available. We've never gotten to talk about it before, called LangServe. And what this will allow us to do is create our apps, but keep our model code separate from whatever user interface you are using. This is very, very nice and convenient. So let's go ahead and jump into it. Okay, so first of all, why deploy your app in the first place? Maybe you have some code, it's doing something for you, it's generating responses based on a document that you have, and it's running fine. You can pull it up on Colab, you can pull it up on your machine, hit play, or however you do it, and it runs great. Well, one reason you may want to deploy your app is to make it available to others. So let's say that you're not just looking to build something for yourself, you want other people to access it. Maybe you have a target audience in mind, maybe you want to actually publish this somewhere. So you need to deploy that. You need to make it publicly available to others, or maybe just available to people of your choosing. Second of all, making your app available to yourself. So similar to your Google Drive, you can access that from pretty much any computer. You can log into Google Drive, access your documents there. Similar to something like this, maybe you don't want to have to run your app on your computer, on the same computer each time. Maybe you also want to access it on a different computer by logging in or something, kind of making it available to yourself on the cloud or whatever have you. And thirdly, using that same LLM-based solution for different applications. This is where we're going to get into the differences between maybe some past solutions of deploying your app and what LangServe offers, is that maybe you have some LangChain code that pretty much does everything that you want it to. Maybe you want it to generate a poem based on a subject, or a joke based on a subject or something. And that code, creating a poem versus creating a joke, is very, very similar. You don't want to have to create entirely separate LangChain applications for those two very similar things, especially if you want to use the same model, especially if the models only need to take one input, which is, subject area or something, and then it's just going to put different output. So let's say you have these two apps, one generates a poem, one generates a joke based on whatever subject you give it. If you don't use LangServe, you will have to basically copy paste that same LangChain code, install all of the libraries, basically write your code twice. But if you do something like deploying your app with LangServe, you're going to be able to use that same LLM solution, but just kind of tweak it a little bit depending on what different apps. So you're able to access different apps and make those available. And we'll talk, if that's a little abstract right now, we'll talk a little bit about it. And of course, there are many other reasons why you might want to deploy your app. And we'll talk about those. We get a lot of questions about making apps available. So let's dive into it. So in the past, maybe way back last year for AI Summer, or even as far as AI Winter, which we host in January, we would have suggested to you Gradio, or Streamlit. We would say these are great Python libraries for creating web apps, and they still are. And we would tell you, use Gradio or Streamlit, make your user interface. You can host it wherever you'd like. Usually we would say Hugging Face. You make your user interface, and you also put in your LangChain code directly into that Gradio or Streamlit code. You would say, all right, so here's my user interface. Directly into the user interface, here's the code for my model. My model is going to run on this Gradio instance, and it is going to calculate whatever outputs that I need, and then send that back to the user for whatever website I'm creating. But now we have LangServe. I'm very proud of that innovation. So LangServe, this is actually very close to the logo. They use a little parrot logo, and then the I guess serve for tennis or ping pong or whatever. But now we have LangServe, and what this allows us to do is actually take that large language model code out of your app and have it somewhere else for you to access. And so let's go into how we can do that. So LangServe, it is by LangChain, as maybe you guessed by the name or the little parrot, and it allows you to turn your LangChain code into an API. So last week, Sharo took us through accessing other APIs, and also through creating our own LangChain models and chains and invoking different chains. And what this allows you to do is to take all of those chains that you made, all of the model setup and invoking, and turn that into your own customized personal API. So an API that you can access from your Python code. And so instead of saying all the setup of LangChain, you put that somewhere, and then you could say, hey, I want that to run. So we'll look a little bit into that. So it's going to automatically create everything that you would need for an API. It includes endpoints, data validation, documentation. If you don't if you're not an API technical person, don't worry about those first two, but documentation is big. Also error messages, that's big. It's going to create these for you magically. And of course you can edit them as well, but it does go ahead and just initialize everything you would need to set up your own API that you can access, that other people can access based on your specific use of an LLM. That is super cool, and it's very new. So now that you have this API, you can use your custom API in all of your applications, or other people can use it. You can set it up. I think all you need to do is serve that API or host that API somewhere. And in all, this is reusable. You can reuse your code. Like I said, in the past, you would have to, put that LangChain code wherever you want a LangChain app. It needs to have that code embedded into it. But with this, you're able to turn it into an API that you can just call and access. It's more efficient, like I said, because you're not running the same code over and over. And it also makes your code more shareable. So let's say that you and a friend are writing very similar apps. Well, you can, design an API that both of you can access, and make it a little more shareable there. So let's actually talk about hosting your app. So I have this little thing, LangServe plus X. And what this means here is that you're going to be using LangServe to create your API, and then whatever UI, user interface app, you decide to use. So like I said, that could be Gradio, that could be Streamlit, that could be AWS. It could be you hosting it yourself on your own computer and writing the HTML. But so we're going to look at what this actually looks like in production. So like I said, it's going to create an API. Any language can use it. So, whatever your website is written with, whatever, if you want to access it through the terminal, if you want to access it through Python or C or whatever, it's creating an API. And then you're able to access that API in, your web app, your website, local software, wherever you would like. And as I keep saying, it's separating your LLM performance from your user interface code. So speeding things up a bit, a little more efficient. So let's go ahead and get into the differences there. I think I jumped ahead and already talked about this, but so first of all, in the past, Gradio, Streamlit, no LangServe. And in this side, it's LangServe plus Gradio plus Streamlit. LLM code is tied to the app UI. So what I mean by that is that your LangChain code will be in the same file as your Gradio code. And then if something goes wrong with LangChain, your website won't even work. It will error out first. If you need to download a bunch of libraries, you're going to have to download that to your Gradio app. Also with Gradio and Streamlit, all of your functions are going to run at once the app starts up. This is because of how Gradio and Streamlit is built, but it basically takes this one app file. Any functions you have in there are going to go ahead and run and initialize, even if you haven't used them yet, in order to start up your website. So that's a lot of LangChain code that you don't need immediately. That's all just going to run, even though you haven't called it yet. And then you're also going to have to install LangChain, all of its dependencies, OpenAI. You'll have to put your OpenAI key directly into the user interface, which has its own security risks as well. And now over on this side, when we're using LangServe to host our LangChain code, and then using inside Gradio or Streamlit, we're calling our custom API. That API is going to be maintained separately. So let's say you need to edit how your model is called. Let's say LangChain updates, and which it's about to push a major update. Let's say LangChain updates, and all of a sudden your UI code will break. If you didn't already have it separated into API, you can edit all of that API code. You can edit the model that you're using without changing your underlying app interface. These API functions are only going to run when you call them. So you define your API functions wherever your API is living, right? And then inside your actual app, you're calling that out. So those functions are only going to run when you call them. And probably a really great upgrade as well is that you only need to install your custom API. You only need to make sure you have access to that, because LangServe, one of its functionalities is also making sure that all of those dependencies are automatically resolved. So if you need OpenAI, if you need LangChain, if you need some other library, those will be included in the installation of your custom API. I'm going to take a break real quick to look at some of these questions. Let's see. Yeah. So it seems like it will be smoother. Definitely much smoother. And it's very new. So I actually haven't had a chance to mess around with it yet. I think it's still in version 0. They haven't even released, version 1.0 yet. But it's really exciting, and I'm interested to see how it works. So like I said, I don't really have code to show you just yet. But if you would like to learn more about LangServe and maybe try it out for yourself, there's going to be a lot of changes in the upcoming weeks or months. So don't get too attached to whatever code you experiment around with, because it might change. But you can see the LangServe documentation. If you Google LangServe or go to the LangChain website, they have a tab for LangServe and then docs on how to get started in Python. They also have an upcoming update in which they're going to have a hosted version of LangServe. So remember before when I said you need to host your API, kind of similar to what Umang was saying with anything LLM and LM Studio, you need to have your model up and running for other people to access it. Similar to an API, I can't access API code if it's not already up on the internet available. But to have it up on the internet available, I either need a machine running it all the time or whenever I need it, or I need, put it in the cloud somewhere. But with this, LangServe is actually going to be allowing you to have some sort of hosted version of this, where kind of like a LangServe Google Drive, where you can put all your API code in whatever hub they're creating, and then be able to access that API. Very exciting. They haven't exactly said how it's going to work. I could imagine maybe similar to Hugging Face, where you may be able to share different APIs, access different APIs, but I don't know. They haven't released a ton of information about it, but it's open source. So if you want to contribute or see where it's going, you can actually just check that yourself. And then, like I said, it's still, even when they do this hosted version update, there's still a lot of updates that they have in progress. So very new. If you do want to try it out, I highly recommend it, but maybe don't use it in production just yet, just because it's a little unstable at the moment. But super exciting. I'm excited to see where it's going to go. And just to show you, here is what an example of what the LangServe documentation looks like. Got the little parrot. And it has, it's saying, it's setting up all of these endpoints for you. So remember that code with Charo, you had invoke, you had stream. It's setting up those endpoints or functions for you to use. So even sets up some logs and error logs, very interesting. And you can even look at your performance in the playground or in Langsmith, as long as you add your API key. So pretty interesting. And then you can see this where it's saying we will be releasing a hosted version of LangServe. So pretty cool stuff right here. And if you want to get started with it, you can look at the code that they have. I'm not going to show it because I haven't myself experimented around with LangServe yet, but maybe hopefully we'll have a neat demo that we can all look at soon. Okay, so I think we're going to take a break. After this break, we're going to talk about training models and backprops. So go ahead and think of what questions you have about what we have just talked about. With LangServe, with deployment ideas, with data security. It's a lot to consider and very specific to your project. So we're going to take maybe a 5-minute break, let you think about that and absorb this information. When we come back, we're going to be talking about training models, and we're going to look at what's called backpropagation, which is how these models are trained. So prepare your brains for this and come back with any questions that you have, either about what we just talked about or what we will talk about with training. So let's see, it is 18 right now. So let's just do 23. We'll be back. All right, see y'all later. Okay, I hope everyone had time to get a snack. All right, so we are nearing the end of our session today, and I know today was mostly just a lot of information thrown at you. So are there any questions before we continue on with some new stuff?
Can you give me a step-by-step process on how to create an app in LangServe, or is that too much?
Look at it real quick. So most of it will just be on documentation. So first, if we scroll down here, it looks like first you create your API server, and it has some examples here where you're creating something that says some function called add routes, and I haven't really dove into this quite much, but you're setting up your API in one file, and then you are calling it. So client means that that's the person calling the API, and then you can just set it up like a normal API. So I think they're calling it, remote runnable. You're going to put in, that local host wherever you are hosting your API. And then you're able to, so like this one, they set up a joke chain, which is something that they defined in their custom API called joke. And then they can say joke chain.invoke topic parrots. So it's just the same as running any other API that you might in Python. The only difference is that instead of some nice, neat name, you're going to have wherever you're hosting that API. So you're going to be running that code in something else. And then you're just able to use it. So there's a couple different ones, using TypeScript, using curl, and then a little bit more information on endpoints. Yeah. And so Umang's demonstration of using the local host is very applicable here as well. Other questions? All right, so I do encourage you, if you're interested in LangServe, definitely try it out. Like I said, I myself have not tried out the code just yet, but I think it'll be really great for integrating into the apps we'll be developing this summer, as well as, some of maybe updating some of the apps that we have developed before at the DSI. So pretty neat. Okay, so then I'll go ahead and go back to my slides. So now what we are jumping into is training of models, and we are actually going to be taking notes from a course that I teach with our data science master's students called Data Science Algorithms. We're going to go into exactly how these models are trained. So by the end of this, maybe you'll feel a little bit closer to having a master's in data science. But we really feel like knowing these training foundations is really important for working with the models. Even if you're not doing the math, if you're not a math person, don't worry. Even if you're not doing the math or needing to, recite how a model is trained, I think it is important to go over it at least once so that when you're using these models, when you're using them in solutions, you have an intuitive understanding of what the models can and can't do and how the training really affects these models. As a review from what we have learned so far at AI Summer, first, Jesse took us through large language models architecture, transformers architecture, encoder only, decoder only, encoder, decoder, all of that good stuff. What exactly is ChatGPT doing? It's predicting the next token. We also talked about using these large language models. Charo took us through how we can use them in our code, how we can use LangChain or other APIs like OpenAI's API to access these models within our code, how we can use agents, how we can use RAG, all of these things for using LLMs that people have already put out. But what we haven't, oh, whoops, and I'm getting ahead of myself. And then just now, we talked about deploying LLMs. We talked today about what you maybe need to consider with private data, how you can put this on some sort of UI. We talked about LangServe, which is very new for turning your code into an API, putting those onto an app. Now, we're going to talk about training large language models. So before, when you were using large language models, someone else trained them. Someone else, OpenAI, you know, Facebook, whoever owns this model, trained it to be able to perform so well. And then when you are using that model, you're using an already trained model. You haven't done any training, any fine tuning for your subject matter or what have you. It is a finished product. So we're going to look at how those models are trained. Today, we're going to give an overview of training, how exactly it works. And then on Wednesday, we're actually going to get into how you can train a model. So today I'll be talking about how the training process works. So when you're working with ChatGPT, you can better understand, how has it been trained? What does that training look like? Why does, do certain things work and certain things don't? And then on Wednesday, we're actually going to take you through training the model. So if you want to get more in depth and train your own models on your own subject matter, on something specific, on something completely new, then you will have that foundation of understanding the theory behind the code we'll go over on Wednesday. Okay, so for some context to understand training, and this is mostly the theory we'll be going over in regards to training. To understand training, we need to understand what is called backpropagation. And backpropagation is the foundation of how neural networks learn. So neural networks, in this little diagram, you can think of a neural network as a model that is kind of structured based off of the human neuron. And we've got these little circles representing one neuron, and they are each connected and sharing numbers between each other. There's calculations going, and we'll get more into that in later slides. But we're going to have this process called backpropagation, in which we are correcting the small errors that occur with each neuron until we get a full network that can perform the task that we want it to do. So backpropagation, when someone asks how are neural networks trained, how do they learn? The answer is backpropagation. The answer is backpropagation. Okay, and then understanding backpropagation is going to allow us to answer questions that we get all the time at the DSI. Maybe some of you have thought of these questions or even asked these questions. And they're very great questions, and I think this will kind of solidify that for you. So answering questions such as, does ChatGPT learn from my queries? Like when you are interacting with ChatGPT, is it incorporating whatever you're saying to it into its learning? Is it learning? Is there backpropagation happening there? Why can't I correct ChatGPT? Like, why can't I say, no, this answer to that is wrong? And then the next day you come back and it still gives you whatever wrong answer. Why can't you correct that? Why doesn't ChatGPT know about recent events? We get this a lot. Why doesn't ChatGPT know how to tell me how to code in LangChain? Well, there's a reason for that. And we'll get into, when was ChatGPT trained versus when did LangChain come out? Oops. So answering all of these questions that we get all of the time. So, they're not bad questions. They're actually great. It shows that you're on the right track. Or Charo, whoever put that in there. Okay, so let's get into backpropagation. So first, and I have a thing telling me my internet connection is unstable. So please do let me know if you have trouble hearing me. And maybe I will turn my video off if I need to. Okay, so first off, let us dissect an LLM for a second here. This is from Jesse's slides, which is from a very nice book on natural language processing with transformers. And what you see here is our classic transformer. So we put in some text, we do token encodings, token embeddings, positional embeddings, and we have this encoder stack, and then we have our output over here. Hopefully we remember something about this diagram. What I like about this one in particular is it's going to zoom. This diagram is zooming in here on this encoder block. It is zooming in on what exactly is happening inside this encoder block. You see something that says, an input, multi-head self-attention, feed forward, and an output block. What I want you to notice, feed forward, this is a neural network. So we're going to be talking about training a neural network, and I want you to know where this fits in to, ChatGPT, to encoders, to the models that large language models that we have been talking about. This is where we're talking about. So it's in this encoder stack here. This is where our neural network is and what we are actually training in this section. So let's take a step back, make it a little simpler. I'm not going to put up the whole, layout of ChatGPT or something up here. But what I'm going to put is a representation of a neural network. And many of you may be familiar with this if you have taken a machine learning class before. If you haven't, that's totally okay. How you can read this diagram here is we have different layers. We call them layers, are these little columns here of circles. And like I said, these are it's supposed to emulate or represent a neuron in a brain. And you've heard neurons have some sort of activation, and then they have an output or some sort of signal that goes out to other neurons that tells you to be happy when you see a kitten, something like that. So these are neurons that are all going to send signals to each other and hopefully eventually arrive at some output that is what we want it to be. So the next token, we want it to be the correct next token. We don't want it to be a bunch of gibberish. We want it to be a full sentence. Or if it's, classifying something, we want it to be the correct class. Like, is this picture a cat or not? So we can look at these, and this is our input. So it says input layer. So we can see this is our input. In this case, we have 2 inputs. You don't really have to worry about the number of those right now, but this is our input. So what we're sending to our model. This is what we're calling the hidden layers. This is when we make the structure of the LLM. You don't have to worry about that. But hidden layers are, some sort of calculations happening in the middle to transform our input into our output. So taking it back to, a neural, to a transformer, for instance, maybe we have the time flies like an arrow over here. And then eventually it goes through all of this positional encoding, goes to this encoder stack. So here we go in the zoom in simplified version of the encoder stack. You have this input. We're going to do a lot of calculations in this here. And then we're going to have an output, which is hopefully, the next word that we're wanting, or, a classification or something like that. And when we're using a neural network in production, what it's called when we give it an input and ask for the output is the forward pass. This is called the forward pass because we're going forward. We're going through the network. We're sending the input. We're doing a bunch of math in the middle and just doing, one after the other calculations that the neural network has, encoded into itself, and then getting that output. So maybe, whatever your output needs to be, then, like I said, the next token, a sentiment analysis or something like that. But so this is for in production. This is when you're using ChatGPT as it is. You're not training ChatGPT, you're just using it as in production. You're using whatever model in production. It's just going forward. We're just sending the data through and performing calculations on them, getting those outputs. But when we're training the models, we got to start from somewhere. We start with, some random, these neurons are initialized with something called weights. That's how these, they all perform some sort of calculation with a weight on them. So you can think of it as a weighted average, maybe. And so all of these are sending their calculations to the next one, combining all their calculations into this output. But you have to start from somewhere. And a lot of times when we initialize them, we're just initializing these weighted averages as completely random weights. So we don't know, what features are important in a sentence. We don't have a lot of information. So we do the forward pass with some random initialization of these numbers, and we get our predictions. As you can expect, if you're just randomly doing this, these predictions are going to be wrong. So what we can do then, because we're training, so supposedly, if you have your training data, you have what the output should be. So let's say in terms of training large language models, a lot of times we have what we call masking, in which we hide one word in a sentence, and then we ask the neural network to guess what that hidden word should be. Of course, we know what the word should be because, like I said, we hid it. We already have that sentence. So then we can then compare the two. So what word did the neural network say it should be versus what word should it actually be? So we can get some sort of, comparison of the prediction versus that true value. So we have some comparison of prediction versus true value. There's a couple different equations you can use, but we're just going over, theoretically, a broader sense right now. And then what we can do with that is we can actually see what went wrong in each of these calculations in this hidden layer here. So we get our predictions. We get our predictions versus true values. And now we're doing back propagation. And back propagation, if we take that word apart, we've got back, moving backwards, propagation, propagating the error backwards through the network. So we get this difference between the predictions versus the true values. We're going to do some calculus on them and find out what exactly went wrong in our calculations to produce that incorrect answer. And we are going to send that back to these neurons. So that's why it's called back propagation. We had forward pass, we're moving forward through the network. Back propagation is moving backwards. As it goes, we're going to know how much we can tweak each of these calculations occurring here to arrive at a better answer. So these red arrows are representing the error, the amount of error that I'm putting back into the network and saying, how can I change this node? How can I change the weighted average that's happening with these nodes to arrive at a better answer? And we put those back through the layers, however many hidden layers you have, until we arrive back at the beginning. So all we're doing is we're showing, how much we can correct our network here. And that is what's happening under the hood when we say we're training. We're talking about back propagation. We're talking about sending it forward and then going backward and correcting each node as we go. What this is going to look like then is a forward pass and then back propagation and a forward pass and then back propagation. So you're going to go forward. You're going to see those predictions versus the true values. And then you're going to say, okay, now I know how I can make my network better. And you're going to incrementally make the network better using back propagation until we arrive at some sort of production ready output. So when your output is good enough, there's a lot of metrics going on in this, a lot of math going on in this. But once you reach a point where you can reliably say you are happy with your neural network's output, then you release the production version. This production version is not going to do back propagation at all because that's a lot of calculus, that's a lot of work, it's a lot of calculations. And you no longer, in production, you no longer have a correct answer, right? So when someone asks it to write a poem, there's no longer, a correct poem that it should output. It's nothing. You're just asking it to create something from the void. And so there's no correction that you could do. So this is why when you get something from ChatGPT, it's not going to constantly correct itself based on what you say to it because it's in production now. It's just doing this forward pass. Mathematically, it has no way of doing this. It has no way of back propagation because it's not in training. They have released the production version of this. And so it's just going to do the calculations that it corrected it, that someone corrected on, someone did this training process. Those are the calculations now. And this is going to create the output for us. So questions so far, we've got about 15 minutes left and we've mostly done what I wanted to, but I want to take a break there because that was a lot for our brains and see if we have questions right now. Why is it called a hidden layer? That's a really great question. And I don't exactly remember the exact etymology of it, but we call it a hidden layer because it's very easy to see the input layer. That's just the data you're sending it. And it's very easy to see the output layer because that's exactly what it puts out. But in the middle here, all of these calculations are a little bit, hidden. They're a little bit obfuscated. Because you're not getting the exact output of this node here because it's going to mix and send it to all of these nodes. So, then the output of this node is dependent on the output of this one and this one and this one. And so it's a little obfuscated. I think that's why they call it the hidden layer. But in short, you definitely can see the data you send to it. And you definitely can see the data you send out to it. Great question. I love that. Yes. Okay. So great question again. So as someone said, let's take this back to LLMs, and I do have a slide on that. Awesome. Please do keep your questions coming. So back to LLMs. Great transition to whoever asked that question. So when we're talking about what part of the LLM are we looking at? we go back to this, we've got the token encodings, token embeddings, positional embeddings, we have encoder stack. And now we have encoder stack and we have this, notice the feed forward. Now you know what that means. Feed forward is that forward pass. We are feeding forward. This is our neural network. So this is what we're training, is this section here. This is what we're training. The hidden states that you're seeing here is actually the output of our neural network. But remember, we went through a bunch of calculations before this. So technically our neural network is not getting time flies like an arrow. It's getting, whatever embeddings as vectors, right? So it's getting numbers. So it's numbers in, and then technically numbers are coming back out. And then our model, we have these hidden states, and then our model is going to convert that. This looks like a key value pair, so it looks like an encoder model. So what's coming out of our neural network here is actually going to be, probably the embeddings for what it's going to output as words. So hidden states is actually the output from all of these encoder stack models going forward. And someone can correct me on that if I messed up. Awesome. Okay, so how do hidden layers determine what patterns are important without giving it examples of expected output? Okay, so unsupervised learning. Unsupervised learning is picking up on patterns within the data. So you're right. So we have, so for those who aren't familiar, we have supervised learning, in which we have something that's like, this is a picture of a cat, and it's a picture of a cat. This is not a picture of a cat. And we say, all right, now here's a bunch of pictures, and I need you to, and all of them are labeled cat or not cat. And then we train our model. So let's go back here. Train our model, right? And we say, okay, forward pass, is this a cat or not a cat? Oh, it's wrong. All right, now forward pass, is this a cat or not a cat? And we correct it, right? So that is supervised because we've given it labels. Self-supervised is when we talk about, having the masked words. So when we say, I really love blank, and that's supposed to be cats. I love cats. I really love cats. And we want the model to guess that word is cats or something. Now, unsupervised is when we just give our model data. So let's say we give our model pictures of cats and pictures of turtles, and we say, learn something here. That is a bit trickier to exactly say what the model is learning sometimes. So yes, thank you, Sharo, for correcting that. I am talking about supervised learning in this case. But if you want to know about unsupervised learning, it is kind of finding patterns. So we may not know exactly what it's finding on what it determines to be a cat-like or in one category, because it's not exactly labeled, right? It's kind of making categories. So I don't want to get too involved into that, but maybe someone in the chat can go more in depth. But yes, what I'm talking about today is a form of supervised learning. Okay, Jesse mentioned week 1. Hey, yeah, so I really love this question. Jesse mentioned in week 1 that the time-intensive nature of early training was a barrier to AI advancement. As the available models become more robust, does the potential for individuals training their personal models grow? So yes, I love this question. So it is kind of like the economy of scale when you think about our cell phones here. So creating this was probably very difficult to create the first one, right? But then once that first one was created, we had something to go off of. And now you can get a phone for way cheaper today than you could when these first came out. Kind of similar to these models, getting that initial training, buying the hardware to train, taking the time to train was very difficult. And people have improved it to the point where it is easier for someone to train their own model than it would have been in the past. Another thing that I want to touch on with that question, though, and why it's really great, is what we'll talk about on Wednesday and Friday is actually fine tuning, in which you're not training the model from scratch. Like I said, remember earlier, I said these hidden states when we're first training are, these hidden layers are randomized because you don't have anywhere to start. But now we have somewhere to start. We have models that perform really well. So if you want to fine tune or specifically train your model on your data, you can start with a model that is mostly trained, then train it the rest of the way on the data that you want. So it does make it a lot easier now. It does make it a lot easier. And as models become more generalizable, as they're able to, encode or talk about more information, I think also the need for training at an individual level goes down. So it's kind of both. Maybe you don't need it anymore, but it is a lot easier. Okay, let me see if I can get through some of these questions. Okay, people are answering the supervised and unsupervised. Thank you.
And might want to point out that that all training of LLMs is supervised, even though we call it self-supervised. That just means that we are masking some of that information, but we know what it is, so we already know the label. So it's self-supervised in the fact that we didn't have to generate the label; we're just masking part of it and calling that the label. But it's all supervised. So you don't really start with like unsupervised training of these models. It's all supervised. We talked about the base models being trained because they're doing just in that guess the missing word. And then we can do additional types of training after that. That might be instruction fine-tuning or alignment or all those things. It's all supervised, a kind of supervised training though.
Right. Thank you. Okay, great. So do keep putting your questions in the chat. A good reading list on the subject. Oh yeah, we've got lots of reading lists on the subject if people want to put stuff in there. So let's go on to what your homework is. So I went over kind of the overview of training, backpropagation. Backpropagation is pretty much what we mean, when training is happening, we're talking about backprop a lot of the times. So go ahead and watch this amazing video by 3 Blue 1 Brown on backpropagation. I will send out the link to you. And then watch that video. It's a beautiful video. It's got these, I pulled this as a clip from them. They have amazing animations for really visualizing and visually understanding how these models are trained. They've got many great videos if you just want to go on a video playlist or just have a watch party together. But I recommend watching the backpropagation video in preparation for Wednesday. And then also come back with, why you might want to train an LLM personally. Like what would the subject matter be? What would your purpose be for training an LLM? Or if you're not sure what you'd want to train it on, maybe think about how you would train it. Like what data would you give it or something? So really interested to see what you all come up with or think about for next time. Let me go ahead and make sure that I have that link for you. I'll put it in the Zoom chat, and then I think we can put it on the GitHub as well. But you can also just look up on YouTube 3 Blue 1 Brown backpropagation. And that concludes today for AI Summer. We will stick around for office hours. Please do keep asking those questions. Thank you so much. And let me get that link for you for the video, and then we will be dismissed. Oh, I'm so glad. Thank you for the messages in the chat. Y'all are a very interactive group and we love it. It is very great.
Miranda, are you posting the video on the depot or you're emailing us that video link?
I am copying the link right now and I'll put it in the Zoom chat, and then we'll also put it in the GitHub repo for you to click on, hopefully if GitHub is functioning.
Yep. And the links for last week's recordings are also linked up there as well in the repo.
Hi, thanks so much for the great session today. Could I ask a question?
Yes, of course.
I'm just curious about if I want to keep the instruction following capability of GPT-4, but I also want it to adapt to the language pattern on my own corpus. could I do kind of fine tuning using self-supervised learning objective, kind of like fine tuning on unlabeled corpus using like predict next token kind of learning objective? Does that make sense? Sorry.
I'm trying to think through. You said you also wanted instruction fine-tuned, but you want to train on your own corpus, on your own vocabulary?
It's kind of a particular type of language pattern, like showing like critical consciousness kind of thing.
Okay. Jesse, did you have, I saw you on mute.
Oh, well, I was going to jump in after you.
Okay. I was just trying to, I'm sorry, I'm just trying to understand. So I believe you can start from some sort of model that's not instruction fine-tuned. And you can train it and then do the instruction fine-tuning again. I'm trying to think on an already instruction fine-tuned model. I think you can give it if you have the instructions.
And you can always do parameter efficient fine tuning. So there are
Right.
ways of doing, and we're going to be talking about those later this week and next week, of how to train models, which do a couple of things. One, it makes them less expensive to train because you're not training all the parameters. And it also prevents the model from suffering from training as well. So this is the LoRa DORA, and also so recent interesting paper about sort of what the limits of that are. Like they were showing that you can't train a model on programming by just using LoRa, even if you allow it to get big, which kind of makes sense. That's reshaping the learning of the entire model. So you need to be doing back propagation all the way into all of your weights, but then you run the risk of it forgetting the instruction fine tuning that you've done. So that's always the tension. You've trained up a model. How do you get it to not forget the things that it's learned? How do you get it to not forget the things that are important that you've trained on it last, like instruction fine tuning or alignment? And so that's always a challenge. But we're going to be talking about some techniques that will help with that. But that's the differentiator between a lot of these different companies right now that are rushing out and trying to get really good performing models is how do you crack that?
Thanks so much for the answer.
All right, and I do have those links in there. I kind of forgot that he actually breaks it up into 2 different videos. So if you want to watch I highly recommend everyone watch the general video on backprop, which I've linked in the Zoom chat. I'll put it on the GitHub. And then there's also a math-centric one that goes into the calculus behind it if you really want to know about that. Or if you just want to watch, even if you don't know calculus, just watch for entertainment and watch the pretty animations.
Hey, Miranda, I had a few questions. So over the weekend, again, my sector is the environmental and urban planning sector. I created an environmental GPT. I loaded some documents into it and a sample RFQ or a request for qualifications. And I kind of wanted your input on it. I don't know if you want to do a breakout room so I don't, take up other people's time. But I want to create a RAG and we used GPT-4 to chunk the docs and I didn't really get consistent results. So what other ways are there to make this more consistent? And I can show you the original results that I got off the RFQ. And then yeah, like essentially just a more efficient way of creating the RAG.
Okay, yeah, I can definitely take a look at that. Why don't we wait like a couple minutes just to see if people have questions about
The lecture,
questions?
yeah.
Yeah, but definitely, I definitely will make time for that. Maybe like 10 minutes or so. Is that okay?
Sure. Yeah, of course.
Okay, yeah.
I had a quick question. So I have this project which I'm trying to vectorize, which has about 3 million 60-page documents. And I was wondering if there are any tools that you might recommend. I've tried Zilla's before. Um, that was okay, but I don't know if it can handle um that many docs.
I think you could use Pinecone. I believe it's free to begin with, but it does have some paid tier as well. But I would assume if there's any vector database that can manage massive amounts of data, it would probably be Pinecone.
Cool. I'll look into it. Thank you.
Yeah, I think for any vector database, if you're dealing with massive amounts of data after a certain point, you might end up finding yourself in a paid tier.
Okay.
And in the homework from Wednesday, I think there is a link to a page on LangChain, which is integrations with vector stores. And although you don't have to use LangChain with them, it does list like tons of vector stores, some of which are commercial and some which are not. And so I think inspecting those, you can learn a little bit more about what kinds of vector stores and like retrievers are out there, just to get like a list of some that you can explore.
And I put that link in the chat.
Thank you.
Yeah, also depending on the type of documents you have, if you were dealing with SQL databases, they have specific vector stores for different data types as
Yeah,
well.
these are all just PDFs. Some of them are scanned, so they might need like an OCRs.
Yeah, if they're scanned and they're not immediately computer readable, you will almost certainly need to do some OCR on them for them to be readable and embedded correctly.
I'll put out there's some interesting models, work on models that work directly with the scanned PDFs, where they treat it sort of as a mix of image, and so they do an embedding of the actual scanned image, which captures some of the text and the graphics all together. Those are still early days, but know that much like analyzing audio. We at first we analyzed audio by getting to doing automatic speech recognition and working with the text. Same thing with scanned documents. Right now, sort of a lot, you go to the text first and then you work with, the text. But know that you can also work with audio directly without changing it into text first. You can work with images and even scanned images of documents directly. But this is just, we're still a little bit early days. The GPT-4o in its full multimodal version does this. It works with images and then works with the embeddings of the images and the embeddings of scans directly alongside the embeddings of the text, and it results in much greater and richer information. So just want to put out there.
I've seen how like MNIST works with like numbers just because there's only 10 digits, but how does the image embeddings work? Like, how are you supposed to know what an image is based on just looking at it.
So you're not. So think about text, right? And so you do an encoding. The first thing that you do is you do your tokenization of the text, and that's clear. But then you do the embeddings. But now you have this high dimensional vector, which represents the meaning of the text. So same thing with images. Now you have this high dimensional vector, which represents the meaning of an image. So it's not like MNIST. MNIST is very close to the raw data, and it stays close to the raw data, right? In this case, you're going into a very high dimensional semantic space. There's no easy way to sort of track it through.
So do you think that that would ever be able to, I don't know, like I'm just thinking back to like my freshman material science class, like understanding a stress strain graph, that could be very easily misconstrued for a different kind of graph. Um, how do you go about differentiating between very different yet visually similar graphs?
It's very interesting to try out and to experiment with. I would encourage you to try those GPT-4o. It's all in the context, right? So if you have some text that came before the graph, or within the graph there are some clues about what it is, it greatly informs how the graph is being interpreted. So just by adding a few words, you can flip what the proper interpretation of a graph is. And you see that behavior in the models. Because remember, all these models are driven by context.
All right, I'll play around with it a little more, but I'll be honest, I haven't played much with 4.0. It just released, but
Yeah.
I'll do that.
Hi, my name is Ingrid. I don't have a specific question, but I just wanted to say hi and introduce myself. Hi, Miranda. I'm a child studies master's student, and I'm also a NICE fellow. And I do autism. I'm interested in autism research, and I'm here because Miranda recommended that I take a course, and I'm really starting from nothing, from no knowledge at all. But I'm really enjoying myself. Thank you guys so much for doing this and making it so accessible, and it just is a lot less scary. You guys are so nice. And so it makes it a lot less scary, like just coming into this with no knowledge at all. So I just really appreciate it. And I'm really behind on everything. So because I'm taking main master classes and I'm doing lab and internship. So I can't be present at all the classes, but I've been slowly working through the recordings and the assignments and stuff. So I'm sure I'll be back with some questions, but thank you guys so much.
Absolutely. And welcome. I'm so glad that you're joining us, especially with being so busy. Keep in mind, we'll also have AI. We'll have an AI training day in March, like March 4th through 6th. And so there's going to be opportunities there. Before then, we'll have AI Winter, which will be a really short version of this. But you can always come back. You can go through the recordings. AI Fridays, we will be around at the beginning of the semester. Every Friday, I think 10 to 12. We still have to set the hours. You can just drop in, ask any questions. Miranda will be there. Anything along those lines.
Okay, that's great. I'm trying to learn right now how to build an app. And so that's where
Right.
I'm kind of coming at this from. So thank you guys. That was really it.
And don't
Yeah,
forget
great to see you, Ingrid.
don't forget to use GPT-4 when you're building or some other. So actually describe what you want, help me build an app. And now you sort of have the framework of like, oh, here are all these different things. So yeah, you're going to be in good shape.
I hope so. Yeah, it's just like I'm coming from special education psychology background, but I think it's so cool to bridge different fields.
Absolutely.
And there's so much exciting potential. So
and also one last thing, sorry, on Thursday there is AWS training day if you are in Nashville or if you want to attend virtually. And so it will be like a ultra fire hose. Okay, not that bad.
What is AWS?
So it will go over a lot of the things that we talked about last week in a really condensed way, except it'll talk about how to implement those things on AWS. So if you're thinking about like, yeah, sorry, Amazon Web Services. So if you're thinking about like a deployable app for the general public, like this is a great way to just kind of jump in and just get all the information sort of at once.
Okay, and even if I'm not caught up on all of last week's Zooms, would it still be used? Yep.
Yep,
Okay.
they're going through all of it.
Amazing. I will definitely try to join. I know you guys sent out some information. I wasn't sure if that was like something that would be applicable or not, but I will totally try to get. Are you guys recording that as well?
I don't think that they record their sessions.
No worries. I'll see if I can hop in. Great.
Yeah, you might need to register for it. So
Yeah.
yeah, just look for that email.
Okay, great. Okay, thank you guys. Bye.
Okay, so Ezra, if you're still on, I'll go ahead and create that breakout room and we can look at what you got.
Awesome, thank you.
Esther, do you need help being you want to be put into that room?
Sorry, no, I didn't realize she created it, so I will go shortly. Thank you.
All right. Any other questions, Ted or Anand?
I'm good. I think I'll just play around with this pine
Okay.
what is it called?
Pine
Pine
cone.
cone. Pine cone.
I don't know why it's called pine cone, but it's called pine cone.
Yeah, I'm not sure either. But I will see you all tomorrow. Thank you so much for today. Take care.
You too.
Yeah. Hi.
Okay.
No questions at the moment, but just to give some context, I work for the Medical Center in Health IT Product Development, and we are just looking at different ways we can utilize LLMs in clinical decision support. So one of the first things that they're looking at is it's sort of like the way that messaging works in My Health at Vanderbilt. When you want to message your doctor, it can take a couple of days to hear back, and where they, you may have some issue, but they need to ask follow-up questions, and that can take a long time if you're waiting to hear back from a doctor to ask the next question and so forth. So it's getting a sort of a interview or questionnaire to be handled by the LLM so they can help diagnose, or at least figure out how they want to see you. So that's the use case that we're looking at, and I'm interested in the fine tuning. I don't know exactly how much of that would be part of the context versus fine tuning a model in terms of how to do a workflow. I mean, a flow chart. If you're asking questions about a UTI or something, and are you having back pain, or do you have a fever, do you have other things like that. So I'm curious to hear if that's sort of embedded in the general knowledge of the LLM, or if that's a context enhancement thing, or if that's a fine tuning kind of thing. So that's where I'm coming from. But I do appreciate all the hard work that went into offering this, and just wanted to say thank you.
Absolutely. One thing that I'll mention in particular about your question is there's been a lot of really nice work around knowledge graphs. And and you can think of that one in a couple of ways. One is to augment the decision making and the operation of an LLM by giving it a knowledge graph tool. And you can think of that knowledge graph as that's one way where it's just a tool. Another way is to think about it as an LLM as an agent. It is operating where you have a knowledge graph which is sitting outside and it's traversing. So it's answering questions and it's using that to actually traverse to get it to a new state. And so it may say, okay, now you're at this point. Here's a summary from the knowledge graph of what's come before, and then here's what might come next. And so it's a way of getting very guided and precise prompts that tell the LLM agent what's supposed to come next.
Okay.
Yeah.
Yeah. Sort of a general question about the ChatGPT interface and sort of what does an actual interface into an LLM look like? Because I know that a lot of what is being, created with the ChatGPT UI is a way to manage the conversation. Like each request to the LLM is in software development we call it stateless. I don't know if that terminology is used in LLM, but there's no consistent conversation when you deal with just the LLM. Like one request into it, that's all the context, and it gives you an answer. Then the next time it doesn't know anything about the previous message. You have to provide that into the context. Is that accurate?
So yeah, so yes, so essentially you have to, so I think maybe Wednesday of last week there's like an example of how you can like store things or store like the different conversations, but you're definitely right where it's up to the user to manage the chat history unless you're using the AI assistants. And then the AI assistants have like built-in things called threads. And so at that point, you're only sending one single message back and forth. And the API itself, now this is OpenAI, so which we can't really like use, but it is managing the history. And so, I mean, as long as there's like an enterprise solution for that, like that's the way that you could also manage the history. If you can get like an enterprise solution with AI, like the OpenAI assistants, where all the history is just stored in one single thread. But otherwise, you can still manage the chat history kind of in a similar way that we did like on Wednesday, but it would probably be better stored in like a database or something, the way that you normally store things in your solution.
Okay, yeah, thank you. So the knowledge graph, would that be something similar to, like maybe the way the threads are working in the assistant, where the context is modified according to the rules of the knowledge graph, but then it's all sort of fed into the LLM as one chunk.
Yep.
Okay.
Context really is everything. There are other ways. Yeah, so currently all the solutions are all about putting specific kinds of information into that context, right? And yeah, so you have it exactly right. So the one way to use a knowledge graph would be to determine what context you want to give to the model. Keep in mind, that like what Shara was just talking about and the different types of agents that you might be able to interact with. Really what's happening there is that they've pre-built like the history of the prior, and they'll actually do a RAG. They'll do a search of like, what are you talking about now? Well, we'll go into our history, see if there's anything useful and pull that in. Same thing with the, with that knowledge graph is, okay, where are we now? What do I need to pull in and what comes next? Or even more than that, an agent where it's like, okay, now what is my job? Right. So now that I've done these other things, I've checked these boxes. Now, what is my next thing to do? My next thing to ask, can provide that kind of guidance.
Okay.
Yeah.
Thank you.
But
Thank you.
that's really the state of the art right now is LLM and then all the different things you can build on top of it. and then interfaces that either go directly into the LLM or go into something which is more and more designed.
Okay, great. Thank you so much.
Absolutely. All right, folks. Any other questions, Ted? Otherwise, I think we're finished up.
I'm good. Yeah.
Okay. And Umang, Abby, and Shara, if you want to stay on for a moment, we can talk about Wednesday. If you want to, is that okay? Bye, Ted.
Thank you. Thank you.
We can do just a quick look ahead, and hopefully we'll have